Hi everyone, I'm Hamin Jung. Today I'm going to present our paper, Replaying with Realistic Latent Vectors and Generative Continual Learning. This is a joint work with Sung Kim and Donghan Choi. So let's get started. In practical applications, GANs encounter a dynamic stream of data. But when we simply fine-tuning a GAN for a new task, it can't generate realistic images of previously learned tasks. So the goal of GCL is to incrementally generate high-quality images as new tasks arise like this. In continual learning, replay-based methods have been popularly used. And generative replay retrains the synthetic images generated from the previous generator, and memory replay uses a subset of previous images in the memory buffer when training the new task. In GCL, generative replay has more often adopted than memory replay because GANs could be typically employed for fitting previous synthetic images. But it gradually loses the GAN's strength to produce realistic images of previous tasks, particularly in complex data scenarios. Memory replay can preserve realism by replaying real images, but it needs a huge memory space to continuously capture the data distribution of all previous tasks. So, our goal is to blend these methods to achieve better memory utilization and preserve realism by combining their strengths and resolving their drawbacks. Our first strategy is about how to utilize the buffer space in a more efficient way in memory replay. We store a realistic latent vectors corresponding to real images of previous tasks instead of storing images. Latent vectors have much smaller size than raw images, so we can utilize memory effectively. We also perform generative replay to further enhance the knowledge preservation by additional synthetic samples. Unlike the conventional generative replay taking random latent vectors, we devised a new optimization technique for latent vectors to obtain more realistic images. So in this work, we've proposed the mixed replay method, rock to fit, to achieve both memory utilization and realism preservation. Rock-to-fit consists of three major steps: buffer construction, realistic optimization, and training. During the buffer construction stage, we utilize GAN inversion to get latent vectors, which are inputs of the GAN corresponding to the previous samples. They are only 4% the size of each image in Cipher10, allowing us to store 24 times more image information. And buffer construction has two steps. First, we update latent vectors in the previous memory. After training the current generator GT with images in this box, we update the memory buffer ZT-1. When we train the next task T plus 1, we only maintain GT, but the latent vectors in ZT-1 need GT-1 to get images. So we could update latent vectors in ZT-1 inverted using GT-1 to the vectors inverted by GT using this equation. And then we invert a particular number of current test task images with this equation. And for inversion loss function, we adopt L1 or L2 norm-based per pixel distance combined with LPIPS metric. Along with replaying images using constructed memory buffer, we also replace synthetic samples using generative replay to further enhance knowledge preservation. And at this point, we carry out realistic optimization to boost the level of realism. And for this, we utilize discriminator, which effectively acts as a learned prior of the real data. Specifically, for each randomly initialized vector z, We optimized Z itself for its corresponding image to get a higher score from the previous discriminator dt-1 by this equation. Mm. As you can see from the before and after results in this picture, realistic optimization is quite effective to generate more realistic and clearer images. So let's say the overall training process. At first task, we just train G1 with the first task images and save the inverted latent vectors of the subset of these images. At task T2, we train G2 with the images in this box, which is a combination of reconstructed images of latent vectors in memory and generated images from realistic optimized latent vectors and new task images. After training G2, we update the latent vectors from the previous memory and newly invert the new task images. And this process is continuously repeated. Now, let's see our experimental results. We evaluate the performance using two metrics, FID expert and fitting capacity. We compare our reactive fit with the following baseline approaches. MER-GAN and DGR are typical generative replay methods, while rehearsal is a memory replay approach. We also consider a mixed replay baseline, which combines MER-GAN or DGR with rehearsal. And CoLLAs2024 integrates additional filtering techniques with mixed replay. We use following datasets and models. And for all datasets, we construct a sequence of 10 tasks, each corresponding to a single class. And we adopt 0.8% and 1.06% of the total number of images as the size of memory buffer. The table shows the results of training on MNIST and Fashion MNIST after completing all continual tasks. A reactive fit shows the best results in most cases and also shows the efficacy in memory utilization. For example, reactive fit 0.8% surfaces rehearsal 1.0% across all cases. And these are the performances of Cypher 10. In GCR context, Cypher 10 is usually considered a challenging data set, and hence MER-GAN as well as MER-GAN plus reassert faces difficulties in maintaining high performance. However, Rectopist is successful in preserving realistic generative knowledge across tasks, thereby without any memory space. Rectopist manages to perform better than rehearsal 0.8%. And our Rectopist generates the most realistic images, as you can see in this figure. As a conclusion, in this work, we've proposed a mixed replay method, Rectopit, which enjoys the benefits of both generative replay and memory replay by making the best use of the input latent vectors of GANs. And by storing inverted latent vectors of real images and optimizing latent vectors for their corresponding images to be realistic, we can improve the memory utilization as well as realism preservation. Our experimental results confirmed Rectopit can extract and transfer highly realistic knowledge across continuous steps of performing the baseline methods of GCL. So this is the end of the presentation. Thank you very much.